Okay, so the first measure of variable importance that we're going to discuss is it's actually a set of measures um, that basically measure the importance of a variable by omitting it from the model. Okay, so this is a fairly intuitive way, I think, to assess variable importance. So if you want sort of a metaphor, okay, picture that you're conducting an orchestra. Now there's many musicians that make up an orchestra, right? But suppose you're interested in measuring the importance of a specific musician within your orchestra. Well, one way to do that would simply be to have the orchestra play a song, right? And then play that song a second time and tell whatever musician you're interested in to simply sit out for that song, right? And, if you were to do this with let's say a second violin in the orchestra, well, there's a lot of other violins playing in the orchestra. So if you told that musician to sit out, it might be kind of hard to tell the difference in the overall sound, right? So you then might reach the conclusion that that particular musician isn't too important to the overall sound of the orchestra. However, if you ask, for example, the bass drum player, or I don't know I forget what these drums are called. These giant drums back here. What is that called? Like a timpani or something? Okay, if you ask that guy to sit out, or you ask the bass drummer to sit out, or maybe you ask the pianist to sit out, well, I mean, there's only one of those instruments in the entire orchestra, and their sound can potentially make a big impact at crucial moments in the song, right? So if you ask that musician to sit out and play the song again, well, then you're probably going to hear a greater effect. Okay, so that's this idea of measuring the importance of a variable by omission. Now, we can do the same thing in our random forest model. Okay, basically remove a variable from the model and then see how that affects the accuracy of the model. Now, in practice, okay, to achieve this, we actually usually don't completely remove the variable from the data. Okay, there are some technical issues why there are some technical reasons why we don't do that. Okay, generally speaking, what we do instead to quote unquote remove a variable is we simply scramble the data for that variable. That is to say, we randomly reorder the rows of data for that one specific variable. Now, doing this essentially destroys the information contained in that variable. It randomizes the information contained in that variable, okay, and makes it basically null and void for the purposes of our model, okay? Imagine taking a sentence and just scrambling all the letters in the sentence. After that, you wouldn't be able to tell, most likely, what the original sentence was, okay? So essentially, these metrics that are about to discuss, they take a variable, they scramble it, and then they rerun the model and look to see how the accuracy of the model has changed. Okay. And so, okay, so let's try this. Okay. So I am going to go back into R here. Okay, and let's have a look at let's have a look at this extra section here. So we're going to be using the home price data set. Okay, we're all familiar with that by now. And so let me go ahead and load up this data set and run my data prep. Once again, we're going to split the data into test and training sets. Okay, you might need to run some of these if you haven't. Pardon me, if you haven't already, you might need to run some of these commands up here to load the appropriate packages. Okay, but after you've done that, all of this code should run. And then we're actually going to fit two models. We're going to fit an OLS model, and we're going to fit a random forest model. Okay, this OLS model, you can see I'm just doing the regular old formula here. I'm regressing on price and all of the other variables in our data set. But I don't want to include V1 because that's just the row number. And then I don't want to include the split variable because that was just used for the purposes of splitting our training and test set. Okay, so these don't really have anything to do with the actual house. I'm not going to include those, but I am going to include everything else. And of course, we are training the model, we are estimating the model on the training set. Okay, so I'm going to do this for the OLS model using the LM function. And then I'm going to do this with the random forest model as well. Now, the only change I'm making to the random forest model here is I'm giving it two additional options. And it's not so important right now that you know exactly what these options do sort of at the detailed level, but we just need to turn them on. Okay, so this local imp stands for local importance. I'm turning it on, so I'm setting it equal to T. T stands for true. Okay, and this second option, importance, I'm also going to turn on T, and I'm also going to set to true. Okay, so I'm going to run both of these models. I'm going to fit my LLS model, and I'm going to fit my random forest model. Okay, so then we're going to call this function. This function is part of the random forest package, and it's var imp plot mod underscore rf. Okay, so we fit our model here. Our model is over here in memory, and then I'm simply going to get it to generate this plot. Okay, and let's have a look at this plot. So I'll make it a little bigger here. Okay, so so you can see there are actually two versions of this plot. Okay, one of these is labeled % increase in mean squared error, and the second is labeled % increase in node purity. Okay, and then we have, notice we have all of these different variables. Okay, and we have some sort of bar graph here plotted for the importance. Okay, so let's just start with the basics. So the higher a variable is on this list, the more important it is. So for example, according to this metric, % increase in mean squared error, this land value metric is the most important. Okay, followed by living area, followed by the number of bedrooms, followed by the age of the house. Okay, over here, according to this metric, the living area is the most important, followed by the land area, followed by the bathrooms, followed by the number of rooms, and then followed by the age. So you can see they don't completely agree, okay, but they both agree that these three factors, the land area, the living area, and the number of bathrooms, these three are the most important in determining the price of a home. Okay, so what do these two numbers actually mean? How are they computed? So let me go back to my slides real quick here. Okay, so essentially, okay, what is going on is it's really pretty straightforward. Okay, so to compute, for example, the importance of the number of bathrooms, the computer does this process where it scrambles that column of data. It scrambles the bathroom variable, essentially, removing it from consideration in the model. Okay, and then it recomputes the entire model, and then it takes down how much the mean squared error changed. Okay, now recall that this mean squared error value, it's one of the metrics that we use to assess the accuracy of the model. The greater the mean squared error, the more inaccurate the model is. The more, the predicted price of the home on average differs from the actual price of the home. Okay, so if we remove a certain variable, then the mean squared error of the model, generally speaking, is going to increase, right? Now, if we remove a really crucial variable, one that's really important to the model, then the error, the mean squared error, is going to jump up a lot, okay? And so the fact that we saw the living area lead to a very great increase in mean squared error when it was omitted means that living area is a very important variable for our model. Okay. Now, the other graph, okay, the graph on the right, it does exactly the same thing, okay, except that instead of measuring the change in mean squared error, it measures the change in average node purity. Okay. Now, you'll recall, okay, that what the random forest model is doing at what the decision trees that are part of the random forest, what they're doing is at each node, they're trying to split the data, and they do it in such a way as to minimize the Gini impurity. They're trying to split, at each node, they're trying to split the data in such a way that the data looks like this or like this, not like one of these in-between values. Okay, and so, okay, so then if you look at the sort of the average degree of purity across all of the nodes in a given tree, that's also sort of a measure of how accurate the model is. And so what this metric is here, the change in node purity, is basically it just tells you if I remove the variable from the model, on average, how much less pure are the different nodes that comprise the decision trees that make up our random forest. Okay. Okay, so I hope that makes sense. Okay, and we will we'll continue this in the next video.